Today I will be teaching you about implicit differentiation. So, why do we use implicit differentiation? Implicit differentiation is used when a function isn't explicitly expressed as y equals some function f of x, but rather implicitly, meaning the relationship between x and y is not easily solvable for y. Let's take the equation x to the sixth power plus y to the sixth power equals 4, for example, which is the equation for this weird rounded square shape with its center at the origin. So as you can see, this equation has two variables, x and y, both on the same side of the equation. So y isn't neatly isolated on one side. And while yes, we could isolate y and find the derivative as we normally would, this might be challenging, time-consuming, or in some cases, impossible. So instead, we will differentiate implicitly by differentiating the equation as it is without solving for one variable in terms of another. So continuing with this example, the first thing that we do is take the derivative of both sides of the equation with respect to x. Okay, so now let's rearrange and evaluate a couple of things. We know that the derivative of a sum is the same thing as a sum of derivatives. So we can rewrite this as this. We also know that the derivative of a constant is always equal to 0. So now we have this. And for this first term, we would just apply the power rule like normal, giving us this. Now here's where it gets a little tricky. Think of implicit differentiation as simply an application of the chain rule. Here's where that comes in. So we know y is some function of x. We don't know exactly what that function is, but it's some function of x nevertheless. So that means y raised to the sixth power is really just f of x raised to the sixth power. So instead of the derivative with respect to x of y to the sixth power, we have the derivative with respect to x of f of x to the sixth power. And we know how to differentiate that using the chain rule. Remember, when using the chain rule, we are dealing with composite functions or functions inside other functions. So first, we take the derivative of the outer function while keeping the inside function the same. So in this case, we will use the power rule like normal, bringing the exponent down, and we get this. Then we multiply that by the derivative of just the inside function, leaving us with this, which is f prime of x, or in our case, y prime. So then we can rewrite this as this. Then to solve for y prime, we simply subtract 6 times x to the fifth power on both sides. Then divide both sides by 6 times y to the fifth power. And we get this. And since the 6 cancels out, we can simplify the answer to this. So this is our final answer. So now that you've seen how implicit differentiation works when we can't or don't want to solve for y, up next, I'll walk through a second example to show how this technique applies to messier, more complex equations. Okay, now let's try a more challenging example that involves evaluating the derivative at a specific x value. Okay, so the problem basically says that if 4 times x squared plus 2 times x plus x times y equals 5, and y of 5 equals negative 21, we must find y prime of 5 using implicit differentiation. So our first step would be, once again, to take the derivative of both sides with respect to x. And going term by term, we would once again do the derivative of sums, giving us the derivative with respect to x of 4x squared plus the derivative with respect to x of 2x plus the derivative with respect to x of xy. Evaluating these first two terms using the power rule, we get 8x and 2. And then this last term, we must use the product rule, since it's x times y. So just a recap of the product rule. The product rule says that the derivative of the product of two functions is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. So for the derivative of x times y, we would do the first function, which is x, times the derivative of the second function, which is dy over dx, plus the second function, or y, times the derivative of the first function, which is the derivative with respect to x of x. So just simplifying this a little more, that gives us x times y prime plus y times 1, because the derivative of x is always just 1. Because, if we have this function f of x equals x, that's a straight line, so the slope of the tangent line is always just 1. Okay, going back to our original equation, we can just simplify the derivative with respect to x of 5 to 0, because once again, the derivative of a constant is always 0. So now if we put it all together, we get 8x plus 2 plus this thing which we got earlier from doing the product rule. In other words, x times y prime plus y equals 0. Now from here, we just solve for y. So subtract 8x on both sides. Subtract 2 and y, giving us this. And then just divide by x, giving us this. Y prime is equal to negative 8x plus 2 plus y over x. And so we're not done yet. The problem asks us to evaluate at a specific point. So we're told that some point with the coordinates 5 and negative 21 exists on this line. So we can use that to find what y prime of 5 is. So all we have to do is plug in. Y prime of 5 is equal to negative 8 times 5 plus 2 plus negative 21. All of this ends up simplifying to negative 21 over 5. So that's our final answer. And that's implicit differentiation. In summary, the first step is to take the derivative with respect to x of both sides of the equation. Step 1.2 is to apply the chain rule, or in some cases, the product rule, if that applies. And step 2 is to solve for y prime, in other words, dy over dx. I hope this was helpful.